2.4 Intrinsic Semiconductors. Semiconductors can be classified as intrinsic semiconductors and extrinsic semiconductors. For an intrinsic semiconductor is made of pure semiconductor, and there's only one element of it. The example is silicon crystal. And for the extrinsic semiconductor is opposite of intrinsic semiconductor. It is a semiconductor compound and made of more than one element. One example is the gallium arsenide. Now let's learn a very important topic in this chapter. It's called the flow of holes. This picture illustrates a piece of silicon compound. The compound is made of a few silicon atoms. And then we place this compound between two metal bars, the two metal terminals. After that, we supply voltage to the two bars. On the left-hand side, the bar carries positive charge, and on the right-hand side, that bar or the terminal carries negative charge. Therefore, there is an electric potential difference, the voltage between these two terminals. Since the left terminal carries positive charge, it attracts the electrons in the compound. The positive terminal pulls the electrons away from the compound. As you can see, that electron move away from the compound and then stick to that terminal. And this creates a hole in the compound. This hole carries positive charge. Also, there are more positive charge on the left-hand side due to the terminal. So the electrons to the right is being attracted by both forces. The electrons move towards left, and at the end filling this hole. Now the new hole is being created, and this hole also carries positive charge. With the very strong positive charge due to that terminal, the electron to the right is also being attracted by positive forces. And that electron is being pulled and then moved to the left, at the end filling this hole. Now a new hole is being created. Due to the same reason, the next electron is being pulled and moved towards left, and at the end filling this hole. And then the following electrons continue moving to the left and filling that hole, leaving there's a hole on the right-hand side of that compound. Because the terminal on the right-hand side carries negative charge, the newly created hole is close to it, and it carries positive charge, so they attract each other. This makes the current hole position very stable. The yellow curve here shows the path of the creation of the holes. Actually, we can think of it as like the moving of the holes. It moves from left towards right, and this is actually the electric current, because the conventional current is defined as particle that move from positive terminal towards the negative terminal. And we also label the electrons movement. It starts with the first electron leaving the compound, and then A moves to that hole being created, and then B continue moving, C, D, E, F, and G. This is the electron flow in the semiconductor material by activating it. And we already know that in order to activate a semiconductor material, we can simply supply voltage to it. The direction of electron flow and the conventional current, which is the movement of the holes, are in opposite directions. They are from the left towards right. From the first hole being created, and then recombination take place. So the hole at point A being created, and then at B, point C, D, and then E, F Eventually, the hole was being created at point G.